So, welcome to everyone. And thank you for joining this seminar. For those of you who still don't know me, my name is Mauro Isaja, and I am a research area manager at Engineering and Informatica. And the research area that I manage is actually distributed ledger technology and digital identities. And this is the reason I am now involved in the Interq project as the leader of package 6, the trusted framework. The reason we are having this seminar today is that the whole concept of the trusted framework is based on blockchain technology. So as we are aware that not many people are familiar with this technology, with this concept, we just want to give you a very basic understanding of what is this all about. So the name of this seminar is a gentle introduction, because actually it is a difficult subject to be grasped. It is quite difficult from the point of view of the technicalities, but also the business perspective is not always clear to everyone. And this is the reason why it is also difficult to get the best out of blockchain. There are quite a lot of pros and cons, and sometimes they are more relevant to your own context, and sometimes they're less relevant. And sometimes blockchain is simply not the right way to go. Anyway, most of the times when you use a blockchain, it means that you are actually changing the way you are doing your business, the way you are managing your process. For today, we have a few learning objectives, not so much because we have just 1 hour, and we also have, if possible, a few minutes for questions and answers at the end. So we are going to introduce some general principles, what a blockchain is, and why do we need it in the first place, and what are the shortcomings of blockchains, because as you will see, there are many. And to do this, we will need to have a look under the hood to understand how it works. And finally, very, very briefly, we will also have a look at what blockchain is going to do in the context of the project. And so we're talking about the trusted framework scenario. Of course, today we are going to focus on the big picture. We're not going into the specifics of the project because, as you might already be aware, we will have a dedicated workshop for this next week. So today we are just focusing on the understanding the basics, okay? So that we can start next workshop with a more solid background. So let's start with a formal definition of what a blockchain system is. Don't worry, because we will get more practical in a couple of minutes. First of all, a disclaimer. You have probably heard about distributed ledger technology and blockchain being used in the same context. They are not exactly the same thing. Distributed ledger technology is a more general term, while blockchain is a specific way of doing distributed ledgers. However, we will focus on blockchain today because that's the most interesting and innovative aspect of distributed ledger technology. So what is a blockchain? A blockchain, formally speaking, is just a distributed system of record that is made of several peer nodes well, at the very least at 2. But it doesn't make much sense to have a blockchain with 2 peer nodes. Usually you have a great number of peer nodes. And together, all these nodes maintain a common distributed ledger that is a record of user transactions. There are a few points that need to be understood very well in this context. That every node, we call them peer nodes because they are equal. Every node is functionally equal to all the others. And every node maintains a complete copy of the distributed ledger. And the nodes are able to exchange messages with each other only using peer-to-peer protocols. So there is no central service, there is no hub. It is a totally decentralized way of working. And then the transactions that are stored on this distributed ledger represent some kind of user input. So we have the peer nodes, which are the infrastructure, but also then we have the clients of this infrastructure, and these are the usually there are applications that are creating transactions. These transactions are probably affecting some sort of a shared state of the system, and the ledger is just the record of every transaction. And the reason why the blockchain is called like this is that the transactions are grouped into blocks. They're not stored individually on the ledger, but they are aggregated into blocks, which are basically an atomic unit of storage on the ledger. And there is a continuous process that adds new blocks to the ledger on a periodical basis. And every block will contain a certain number of transactions, might be a few, but might be even 1,000. So in all transactions when they are created by a client, they are simply queued to the system until they can be included in a new block. And the point is that to be included in a block, a transaction must be validated. So you only find valid transactions inside the block. And last but not least, these blocks, not only they are immutable because you cannot change whatever is written in a block after it is written to the ledger, but they are chained logically. So that you have a new block with a logical pointer to the previous block. And this is the reason why we talk about a blockchain, which is simply a chain of blocks. Now, it might be a bit confusing, and so we are going to get a bit more practical, more concrete. And so we can summarize what a blockchain is in practical terms in 3 ways. Firstly, a blockchain is a collaborative network of autonomous stakeholders. So whenever you hear the term decentralization referred to blockchain, this is the point. And the choice of these terms is not by chance. You have, of course, a network because all the stakeholders are connected with one another. It is a collaborative network because the point of joining the network is to participate in a collaborative process. And all the stakeholders are autonomous. They are autonomous because there is no authority in place. So everyone is an autonomous entity. And the last but not least, they are stakeholders because there is something at stake. Okay, so they have some business in common. and we will see more on this later. Generally speaking, the stakeholders of a blockchain system will operate a peer node. So this is the way in which they can actually engage in this collaborative network. They have to operate a peer node. So when you hear about something called blockchain as a service, or which is basically a blockchain that is operated on the cloud by some service provider, or even you might have heard of blockchain systems that are operated by a single stakeholder, a private blockchain internal to a company. Well, this system is really pointless, except for one use, and that is when you need a sort of a sandbox because you want to experiment and you want to be safe and you want your experiment to be cheap. You don't want to invest in infrastructure, and then it makes sense to have a sort of blockchain as a service. And this is, by the way, exactly what we will be doing in this project to provide the pilots with a blockchain that they can use without the need for operating a peer node, because we understand that this might be too much. So we will provide a blockchain as a service in Interq. Then, second point, what is a blockchain system? It is a permanent and highly available memory space where you want to store critical information that must be shared among all the stakeholders. So, of course, if you don't have anything to share, there is no point in having a blockchain at all. And let's not forget that permanent and highly available are two adjectives that are really relevant in this case. First of all, because whatever you write on the blockchain is there forever. So you might have something like a logical deletion of a record, which means that you write another record that tells that the previous record is not more valid, but both records will be there forever, for everyone to see, by the way. Highly available, because this is a distributed system. So every node of the system will have their own copy of this memory space. So it is perfectly okay if one or more nodes are offline because for any reason, because they are broken, because they are not connected to the network, but you will still have access to your entire ledger. Unless, of course, you lose a significant amount of nodes and then the system is unable to work anymore, but we will see that later. I say here that it is nearly impossible to alter individual records on the ledger. I say nearly because actually it is physically possible. If all the nodes or a majority of the nodes agree to alter the ledger, they can do that. Usually that's not the case. And it is very difficult to find a good rationale for doing that, although I have seen happening this in the past. But let's say that in speaking in general terms, it is impossible to alter individual records. Another important point, the second one, is that records are public. Whoever has access to the network can see all the records on the ledger. So if you think that you need to regulate access to records on the ledger based on identity, on roles, this is not the right technology, because the main point of a distributed ledger is the information is public for everyone. which doesn't mean that it is public in absolute terms, because if you have a network that is, as we will see later, a permissioned network, so you need to be granted permission to access the network, then you will have indeed a restricted memory area. But inside that restricted memory area, everyone will have the same access rights. That said, the records on the ledger might mean something individually. If you just want to record some information that is meaningful by itself, that's okay. But there is also the case frequently that you're recording transactions on the ledger that are changing a sort of common system state. And so every record is just something that is added on top of the other, and the sequence of the record is what makes the system state. Finally, third and last point of what blockchains are. This is something that is, we hear this very often. They are an enabler of trust in adversary environments. What is an adversary environment? It's an environment where you cannot trust anyone. But as long as you trust the system, then you can trust that what is written on the distributed ledger is fine, is correct. Unfortunately, as we will see, this role of a blockchain system is only possible in some very specific cases, in particular when the network is public. Otherwise, we cannot say that the blockchain system is an enabler of trust at all. Okay, so having said that, let me make a step backwards and look at the very beginnings of blockchains, because I think that in order to understand what blockchain can do, it's probably a good idea to understand what was the need, what we can say the business pain that the first blockchain system was addressing. And that was all about finance, and in particular about digital money. It was not just because there was a need for an electronic payment system, because there were a lot of them already at the time. But the main point was to replace the regular money, so the money that is minted by a central bank, with something different that is not under the control of a central bank, of a government, or anyone. And the reason why this was done, because there was a perception, at least, that the very value of money is influenced by government through the policies, and government policies are usually inflationary, which means that savings will lose some of their value over time. And also government can indeed limit the use of cash, because they can control the flow of electronic money. So basically they can monitor the flow of money. And this is a big form of power. And the people that were considering this as bad things, let's say, were usually in a very specific philosophic field, which is the so-called libertarian field. And if you don't know what this means, you can Google that up. But okay, they are basically a group of people who think that the ultimate solution for everything in finance is to remove the government and leave market forces free to do their job. So in their eyes, there was the need for a radical solution to this problem. And so the idea was to create a new form of money that was a commodity like gold, for example, but was entirely digital. And so it was suitable for doing transactions online. And so in order for this to work, digital money to be actually a commodity, there were some requirements that were needed for this system. And so there should be a predetermined and fixed supply of this commodity money. Transaction had to be trustworthy. Users should be totally anonymous. And the system should be censorship resistant. And this is exactly the definition of a cryptocurrency today. And by the way, that's Bitcoin. So the very first blockchain system was Bitcoin, as you probably know. Now, this might seem a little nerdish, and indeed, initially it started in a garage. But today, as you all know, it's a very big business, and these are some numbers that you can see. On the left-hand side, you see the value of the Bitcoin, the market value of the Bitcoin that started nearly as zero and reached a peak of nearly $6,000 American dollars, and today is around 40,000. Also, you can see on the right side the so-called market cap, which is an interesting number because it means the total amount of Bitcoins that are circulating today, and it is the order of magnitude is 1 trillion American dollars. So this is really big business. And also you see it from the number of transactions per month. In 2009, where the Bitcoin system was firstly put online, there were around 3,000 transactions per month, and we have 10 million today. And okay, this is of course all related to finance, and it is not immediately clear what this might mean to regular business and, for example, for manufacturing. But the point is that when you have something like a decentralized system for transaction, for online transaction processing, you can also exploit the same properties of the system within applications that deal with generic data instead of transactions that move digital money from one account to the other. And the trick for doing this, to turning a blockchain into a generic platform, is to modularize the business logic. In the first system, Bitcoin, the business logic of transaction was built in the system, was basically hard-coded into the blockchain client, that the business logic was just about telling the system to move a certain amount of Bitcoin tokens from one address to another address. But if you turn this into a modular system where the business logic is a program that can be written by a user and deployed using the same mechanism to validate transaction, then you will have a way for running distributed applications on a blockchain. And so you have what was called initially smart contract, which is the name that was given to this model by the Ethereum platform, which introduced smart contracts firstly. I think in 2014, if I'm not wrong. The Ethereum platform was still a cryptocurrency system, by the way, but it also is a platform for running applications that might have nothing to do at all with the cryptocurrencies. So a smart contract defines their own data model, their own transaction format and semantics, and the data that represents the application state of the smart contract is persisted on the distributed ledger, which is on the blockchain. And there are many possible uses of this technology, but at first it was not totally clear which were the most suitable use cases for this new innovative technology. And some years ago, there were a lot of people experimenting with blockchain in several different areas. I am quoting here a study for Moody's Investor Service, which is quite, it is very, I mean, this study was quite popular at the time. You might have seen this slide in a lot of places if you followed this discussion. And these were, according to Moody's, the most promising areas for blockchain. And I just have highlighted the supply chain management because it was clear since then that it was a good use case. But now that we know a bit more about the technology, we also understand that some of these were a bit naive. Like, for example, big data and data storage for sure are not good use cases for blockchain technology, as you will understand shortly when we will talk about how the blockchain works internally. And so this was also the question: can we dump the cloud, given that we have this fantastic new technology that is catching up? Well, no. We cannot dump the cloud at all because blockchains have quite a bit of shortcomings with respect to traditional, the classic applications, cloud or not cloud applications. And you can see here a complete list of them. This is taken right from deliverable D1.4. If you want to know more about this topic, I strongly suggest you to read it. We are not going into detail here about this, but of course, now we are going to start looking inside the working of blockchain. So probably you will be able to understand by yourself why, for example, scalability and storage efficiency are not the best points of blockchain technology. But again, for those of you who have an interest in understanding better the topic, deliverable 1.4 is for sure a good read for you. So now we are going to dig a bit into the technicalities. It might be a little boring, but I think it is really important to understand the basic mechanism, because with this understanding, it will be possible for you to make good choices for your business. So, first of all, the original concept requires a permissionless network. You will be hearing this quite often: permissionless versus permissioned. In a permissionless network, all the users are anonymous because there is no notion of identity. So it's not that we are hiding the identity. We are not asking the identity to anyone. And so nothing prevents people with a suitable client or a suitable peer node implementation to connect to a network and work on that network. And all the cryptocurrency systems are permissionless, because this is a requirement for meeting the anonymity of user and censorship resistance points of the list that we have seen before. But then there is also another requirement, which is trustworthiness of transactions in a system that has no human governance. So we cannot have someone who decides if a node is performing badly, if he is following the rules or not. We cannot have any human telling if a transaction that is submitted by a client is correct or not. And also we have to assume that everyone wants to cheat the system. And this is what is called an adversarial environment. So we need something that is totally automated and also can be trusted, because this transaction might be a transaction of some value for you. And of course, if you are moving money, this is straightforward, but there might be also a transaction where you are moving data, but it is data of value. So you need a system that will be able to ensure this trustworthiness by design, enforcing transaction rules, even if there might be some attempts by users of the network to hijack the system, so to tame the system to their own advantage. And not only this might be the efforts of some individual users, you might also have to deal with coordinated efforts. And this is very difficult in a distributed and decentralized system. This is a problem that was, in game theory, they were aware of this since a lot of time. And in literature, we have a paper in 1980 that provided a theoretical solution for this, but until the appearance of Bitcoin, a convincing implementation of this was not available. And the way that blockchain technology managed to tackle this problem is to date unsurpassed. So we still don't have any better way of doing it. But unfortunately, as we will see, the way of doing it is also a big burden in terms of performance, scalability, and also functionality. And this is the reason why you don't often see blockchains adopted outside of the cryptocurrency use case. So let's go through quickly the theoretical problem that was formalized and also addressed with a theoretical solution in the 80s. It is called, well, it was popularized in a way with an allegory, which is the Byzantine generals problem. And in this narrative, you have a bunch of Byzantine armies that are sieging a city, and these armies are under the command of generals, which are totally autonomous, but they need to agree on when to launch a simultaneous attack or when to retreat simultaneously. And you can either attack or retreat simultaneously with success, because if this is not well coordinated, then you have a disaster. So the only way for this general to reach such agreement is to exchange messages with one another and to tell what their intentions are. But unfortunately, messages cannot be trusted because they can be intercepted by the enemy. But even the generals cannot be trusted because they may be traitors. They may have colluded with the enemy. And so there was indeed a theoretical solution. How can we reach an agreement with some confidence? And any system that implements this kind of theoretical solution is said to have a property that is Byzantine fault tolerance. A Byzantine fault tolerance system will be able to work in a predictable way as long as you have 3/4 of the nodes of the stakeholders that operate correctly. And so if more than 1/4 of the generals of the nodes are faulty because either they are not operating correctly or they are conspiring to achieve a false outcome, then if there is more than 1/4 of the nodes, the system will be not able to reach a trustworthy agreement, a so-called consensus. And the term consensus is indeed the standard now in the blockchain community. The mechanism through which a blockchain system can validate transactions in a collective way is called the distributed consensus mechanism. Now, in Bitcoin and also in every major cryptocurrency to date, the actual implementation of the distributed consensus mechanism is called the proof of work. It is very, very good at decentralization because we can safely say that this mechanism does not rely in any way on trust on an external entity. It is a system that is entirely trustworthy by design. And by the way, it also performs much better than the Byzantine fault tolerance, because with this mechanism for distributed consensus, we only need the majority of nodes that work correctly. So at least the majority plus one good nodes are enough to say that the system is reaching a trustworthy consensus on transactions. However, this proof of work algorithm is extremely heavy in terms of efficiency of computing, but also because it depends on the existence of a cryptocurrency. So you cannot use a proof of work consensus mechanism unless your blockchain system relies on a cryptocurrency, which might not be the case in a lot of business scenarios. The idea is to use the cryptocurrency to create a balanced system of rewards and penalties for good versus bad behavior. And at the same time, you can use the cryptocurrency also to ensure the sustainability of the system, of the network. So the idea is that the users are incentivized to participate in validating transaction, because every block, you remember that we said that the block is the atomic unit where transactions are stored on the ledger. So we create periodically new blocks containing transactions, and all the transactions there must be valid. So there needs some node who is responsible for validating those transactions. So these nodes are incentivized to do this because they will gain a reward. But to gain the reward, they need to win a contest. So there is no single validator node. The validator is elected through a public contest. And to participate in the contest, the participants will be sustaining a cost. So basically, they are putting something at stake. And so at the end, when the winner will be creating the new block, in order to claim the reward, this block should not be found faulty by the others. So this means that if you are validating transaction and the transaction you are validating are actually bad transactions, you will not get the reward. And this also means that your stake, so the cost that you have sustained by to participate to this contest, is lost. There was no point. And this is your penalty. So there is a reward and there is a penalty. And to make this work in a scenario where there is no coordination at all, there needs to be a very good algorithm that ensures a fair competition, so that every participant has a chance of winning the contest that increases linearly with the amount of the stake. So the economic investment they are putting in this, which amounts, practical terms, to, as we will see next, to the computing power that you are using to win the contest. Okay, and then on the other side, the reward is a fixed amount. Is a fixed amount in the cryptocurrency that the system uses. So this means that you cannot, as a participant, invest too much to be sure to win at all costs, because you know in advance what your probabilities are and what is the reward. So this means that the system will adjust itself basically based on the value of the reward. And I understand that this is quite difficult to grasp, but if you want a more in-depth understanding of how this works, again, have a look at deliverable 1.4. Now we are leaving it here. Otherwise, we are going in too much depth. Okay, so I think that also we can skip through this slide quite quickly. I just wanted to highlight a few keywords here, because this is something that you might have heard before. The whole process of participating in the contest in order to have a reward is called in the crypto world, the cryptocurrency world, as mining. And the people that are doing this, usually they are doing this as their business, are called miners. Okay, because basically what they do is that they are using their computing power, which is very significant, because in order to win, well, in order to have a good chance of winning the contest, you need really to deploy a fantastic amount of computing power and to consume an incredible amount of energy to power this. And so it basically, it's just like mining. You are investing in tools, and then at the end you extract something from the system. And now the problem is with this mechanism is that it's terribly energy inefficient. And having all this competition currently, and the competition is there because the reward is very big. So if the Bitcoin is worth $50,000, and indeed today when you mine a block, so when you win the contest, you get 6 plus something Bitcoins as a reward. So you're getting really a lot of money, and proportionally the energy consumption to do this, of course, is huge, because there is a huge competition for getting the reward. And the result, the final result, is that the whole network of Bitcoin is consuming an amount of energy that is comparable to that of a mid-sized country like Sweden, which amounts to 135 terawatts hour per year. And this is the reason why everyone says today that cryptocurrencies and Bitcoin in particular are not environmentally sustainable. This is going to change in the long term because there are alternative distributed consensus mechanisms that are being experimented. But today, this is the state of the art. And then there is another big problem with this mechanism, is that it is slow. Transactions take a long time in order to be confirmed. And also, I would say that there is another problem, that transaction may actually disappear from the system, but this is something that probably we will have the chance to see later. So this means that permissionless blockchains in general are only suitable for some very specific use cases, and 90% of the times this means cryptocurrencies. Now, fortunately, we have another technology, which is the permissioned blockchain. And the permissioned blockchain is what saves the day for us, because it is much simpler than a permissionless system, thanks to the fact that we introduce something that we purposefully left out. So we are sacrificing decentralization, because here we rely on some trust that we still have to have in at least a few nodes of the system. And in a permissioned system, we will have user authentication and authorization. In some way, a permissioned system will be in the middle between a permissional blockchain and a distributed database. From the performance and scalability side of the story, they are quite close to a distributed database. But with this only exception of access management, they don't need to be managed centrally. This means that everyone, once they have been granted permission to join, can operate their own peer node in a fully autonomous way without any coordination with a central manager. Now here we have a list of the differences between permissionless and permissioned. I will not go through this because we are quite late, and I don't want to go beyond the allotted time. So I would suggest you to have a look later to this slide deck, which of course will be published. I just want you to have a close look at a few rows, because the most interesting ones are the last four. So the main reasons why we are going to use a permissioned blockchain in any scenario that has to do with the supply chain is because we don't need a true decentralized system, because a supply chain is a business ecosystem where we already know the identity of partners. So we already have some sort of trust relationship with them. We know how much we can trust these partners, and if for any reason we decide that we don't trust them anymore, we can simply exclude them from the system. So this is a huge simplification with respect to a permissioned blockchain. Most importantly, even if we can still not store large volumes of data because we still have the problem that data is replicated on each and every single peer node of the network, but we have a level of performance and scalability that is compatible with a business process, which is not the case with a system like Bitcoin, for example. We don't have the problem of environment friendliness, which is increasingly a showstopper for large enterprises that have also a sustainability agenda, in particular if they are public companies. And the most important point is probably the last, that the transactions on a permissioned blockchain, once they have been written to the ledger, they are irreversible, they are final. While in a permissionless system like Bitcoin, there is still a possibility that the transaction will be reversed. And so this means that you cannot ever be sure if a transaction is committed for good or not. You can basically rely on the fact that if the transaction was there for a significant amount of time, like for example, for 1 day, it is nearly impossible that it will be rolled back. But if it is there since, let's say, 10 minutes or 20 or 30 minutes, then you cannot be totally sure that you have a final commit of this transaction. And this is one of the reasons that the permissionless system as they work today are not a viable option for a business ecosystem. So now it's time to do a short recap of what we have said. Any blockchain, regardless of their permissioned or permissionless nature, every blockchain is not good at these things. They cannot store huge volumes of data, even if on some platforms you can do that, but it's not a good idea because it is a very inefficient way of solving a problem. Also, you cannot run a very complex query on the data that you have stored because a distributed ledger is not a data structure that is suitable for that. For instance, it has not an index. And another thing that you cannot rely on is that the data that is stored there is in absolute the truth. So if you, to make this more clear to you, if you have users that are creating transactions, data transactions that are where the input, the data that is provided in the input is bad because you are basically providing false information, there is nothing that the blockchain platform can do to spot and prevent this. It's the so-called garbage in, garbage out effect. Okay, the only case in which a blockchain application can do that is the so-called self-contained application. And an example of a self-contained application is a cryptocurrency, because all the application state that you're maintaining is just the balance of accounts. And so the input from users is just, I'm moving this amount from this account to this other. And so whatever is written on the ledger can be regarded as the truth. But if you are doing something like we will do in Interq, when we write on the ledger a statement that tells all the other stakeholders in the ecosystem that the quality hallmark for a given product is this, then this doesn't mean that the quality hallmark is correct by itself. But what you do have is the traceability of the statement. And you know exactly who is accountable for the statement. You know for sure that this statement is there forever. And you also know for sure what is the timestamp of the statement. You know for sure at what time the statement was made. Okay, so last but not least, blockchains are very bad in processing input in real time. So if you want to do something that has very strict timing requirements, blockchain is not for you. Also because the timing can vary very much. And so you're not sure if the next transaction will take 1 millisecond to be confirmed or 1 second. So this is not the definition of real time. You cannot do real time on a blockchain. Another important thing is that if you have to process an immense amount of transactions, then you probably want a system that has a very low per transaction processing cost. And again, this means probably blockchain is not for you. What we are doing in Interq. In Interq, we are going to use blockchain technology as the key enabling technology for the trusted framework. I'm sure that now you can see by yourself how this can be true, how this can be a key enabling technology in this context. We are not going to discuss the trusted framework architecture right now, but however, sort of I will anticipate what we will be discussing in the workshop next week. We are going to use a mixed approach for the trusted framework. We are going to use the blockchain for what blockchains are good for, and we are going to use a different technology for what blockchains are bad for. In particular, the idea is that we are going to store data on a traditional, more classic, although federated, distributed persistent service, and blockchain will be used just for tracking and storing metadata. And we will have a very strong identity management system that will be also implemented in a decentralized way on the ledger. The pictures that you see here are also from deliverable 1.4. And so again, I will say this a third time, if you want to know a little bit more about that, that is the right source. Fine, just a bit late, but we started 5 minutes later, so I think I was on time in the end. It's time for any questions that you might have.
I have a question, Mauro.
Go ahead.
Hello, yes, thank you. So thank you very much for your presentation. That was very, very fantastic. I started with zero understanding on blockchain. I think now I got a lot. So I wrote down a lot of questions in the chat actually, but I can see that Patrick tried to answer most of them. I'm very happy and quite happy with the answer. I
have to say that I don't see the chat. So,
okay.
But I can if okay, now let me see. I had just to remove my screen and replace it with the chat. So I'm not looking at the slides now, I'm looking at the chat. Okay, I can see your questions right now. Okay, yes, the answers are correct.
Yeah, I think if the answer is correct, I mean, you don't need to reiterate, right? So it's fine.
Okay, so I also see another question. Okay, so a previous question from yours. The question about open source. Yes, there is, of course, because mostly every blockchain platform is open source. There are a few exceptions, but fortunately, those exceptions are not very interesting for our use case. They are very vertical systems. The systems that we might want to play with are all open source. The system that we will be using in Interq is Hyperledger Fabric, which is open source. It is under the Apache 2.0 license, which is business friendly. And it is also the system itself, the Hyperledger consortium is under the wing of the Linux Foundation. So it's something that is there to stay.
Good.
Okay. Then I see other questions. Let me see. The drawback of real time. Yes, the drawback of real time not being an option is also valid for permission and blockchain.
And even if all nodes are active 24/7?
Yes.
Okay.
Real time is about the predictability of the system reaction. So it's not about how short time it takes in order to respond. It's just about to be sure that the answer from the system will come within a certain time frame. This cannot be possible on a blockchain, whatever the configuration of the system. It is an architectural limitation.
Okay. Yes. Thank you. Then I think I have all the answers. Thank you so much for both of you. Very, very useful. Thank you.
Other questions?
Maybe one point to add from my side regarding the question for if blockchain nodes need to be active 24/7. In a proof of work system, it doesn't matter if node goes offline or not, because there the consensus is reached by the computing power, and if there are less nodes online, the system is less secure and they have less computing power to reach the consensus. But in other systems like BFT or in general proof of work, you have something like a set of validators, and you also have some rules in place that you need to have 2/3 of the node to reach a consensus mechanism. So if you lose more than 2/3 of the node, for example, you will have the problem that the system doesn't work anymore. And in that case, it's really important that you have a infrastructure where all the active validators of the blockchain are able to operate that 24/7, and that you are not going in a situation where you have less validators and cannot store data anymore inside there.
Yes, and this also brings in the light the problem, if you can call it such, that while public permissionless blockchains tend to be big networks with hundreds or even thousands of nodes, and in that case, it is clearly unlikely that you will have a massive outage of a significant percentage of the peer nodes. When we are talking about permissioned networks, usually we have quite a few. We have tens of peer nodes in the best case. And then you have to deal with this possibility, because there might be indeed some scenarios in which you have a big number of peer nodes that are not available, that are not online at the given time. So you need to have some sort of management plan for that.
I have a question also. Thank you for that answer. I have a question which is not yet answered regarding because blockchain using network as the backbone, basically, how does it vulnerability to cyber attack actually as compared to the other?
Say it again.
The vulnerability to the cyber attack because you are using a network
yes.
as a backbone. Yeah.
Now, the vulnerability in a permissionless network is tied to, I would say, the total value of the network itself, because as much the value of the network is high, as much computing power in a proof of work system you will have, because there will be a stronger competition to get bigger awards. This means that an attacker will have to compete with a higher stake. So they will have to overpower the total computing power of at least half of the network in order to enforce their own vision of transactions. This means that if the value of the network is comparable to that of Bitcoin, this would mean that you will have to invest probably billions of dollars. And this is not something that clearly many actors are willing to do. It might be argued that Bitcoin is indeed vulnerable to state-sponsored attacks. Yes, it is. But we already have some good examples of this sort of brute force attack made on cryptocurrencies that are much less valuable than Bitcoin. And in particular, I'm speaking about Ethereum Classic, which is not the Ethereum, the main Ethereum. Is a variant of Ethereum, which has quite a low value in comparison with Ethereum or Bitcoin. And there they have already had 3 attacks of this kind that were all of them were successful. So there was someone who managed to spend a significant amount of money in a 51% attack, and they indeed managed to hijack a bigger amount of money. And so it means that that is a vulnerable network. In the case of a permissioned network, we are not talking about a brute force attack. Here we are talking about having a good supervision of the workings of the. When I say supervision, I'm not talking about an authority doing that. I'm talking about something that can be done in a collaborative way. So all the stakeholders need to be aware that some individuals in the network may not be operating correctly. If that is the case, then as long, of course, as the bad operators are not the majority, because in that case there is nothing you can do. But if they are the minority, then what you will do is that you will shut them down, because the permissioned system allows this anytime. You can grant or you can remove a grant for access.
Thank you. Very clarifying.
Okay, thank you, Mauro, for your presentation. I think that we can close this short seminar. I will like to thank you for this presentation and also to all participants. And we'll be in the next workshop that we will have next week, where we will deepen in the characteristics and we will go in details about how to implement it in the Interq project.
One more thing. The next will be a workshop, will not be a seminar.
Yeah.
So it is expected that after we will introduce, of course, the trusted framework architecture, we expect to engage in a discussion with whoever, I mean, the users of the framework, supposedly, whoever is going to be our customer, let's say. So we are not just providing something off the shelf. We expect to actively engage with you and involve you in the second part of the design process, because we know what will be the basic functionality, but we don't know what is needed to specifically address the needs of your use cases. And this is something that we want to do together with you.
Perfect.
Okay, Mauro. This is Joaquin speaking. So thank you very much for the seminar, and I recommend you to all the partners to read the deliverable D1.4, because I think there is a really good information about this fascinating and trendy topic, and honestly I recommend you, because you have all the insights of many of the other set topics. But one final question for you, Mauro. I think also it would be great to highlight the main, let's say, advantages of the blockchain technology related with the quality management. I guess.
Yeah, yes, we have already an idea of how this should be done in general terms. I have already introduced this topic during the seminar today, because when I said that this is going to provide an accountability environment, an accountable environment for quality data, that was exactly what I was meaning. Blockchain will give to the supply chain the capability that was not there before, and that is that this kind of information that is going to be a common value for the supply chain can be trusted to the extent that you can trust the author, the source. So we are using this technology to give this additional level of confidence without introducing, without the need for a central service, because if you have a central service in place, then you need also someone who is responsible for it. And the idea is that we want to go towards a horizontal, non-hierarchical structure of the supply chain.
So I think this is the best way to finish the seminar, with this message. Okay. So thank you, Mauro, and all the participants, and see you next week. Bye.
See you all. Bye-bye.
Bye-bye. Thank you.
Bye. Thank
Bye
you.
bye.
Thank you.
Bye.
Bye. Thank you.
Thank you.